Is dark matter God? Generally accepted by most scientific and even many religious sources is the theory of the Big Bang. And recently they have really just seen evidence that the universe is expanding as if it was an explosion. And then they came up with a problem and said, well, why is it expanding so slow? Because when they looked at all the stars and in the way that only astrophysicists can do, calculated the mass of what they could see, they said, oh my goodness, we can't see 9/10 of what's out there. Because if it was only the stars, that would already be expanding a lot faster. So what's slowing it down is this dark matter that's holding us together, something we can't see, something that we know is there because we intuit it from our observations. It's ethereal. They used to say that the planets were hung up in the ether, and that was something that was discarded, and now the ether is coming back. And this confuses me, because when I grew up, science was science and religion was religion. Science dealt with the objective and the material, and religion dealt with the ethereal and the spiritual. Science was objective and religion was subjective. Science was observation and religion was speculation. Science asked what is and religion asked what if. Many of us, myself included, have an understanding of science similar to Isaac Newton. We see objects as they move through space. Things are solid, space is empty. Newton developed a theory of how things moved. He described gravity and did the math in a way that allows us to fly. When we drive our car and slam on our brakes, our bodies move forward, just as Newton predicted. Newton described the world from the elements to the solar system. And for most of our day-to-day lives, Newton is all we need. This congregation each spring holds an auction in which someone gets a chance to buy the sermon topic, and Jim Campbell did that, and he handed me 2 books, which he has with him back there, The Elegant Universe and 3 Ways to Quantum Gravity. And so I have been spending recent weeks looking at 2-dimensional representations of 10-dimensional space and trying to figure out how I was going to do that from the pulpit. Thankfully, I found a website that was called SimScience, short for Simple Science. They finally said, oh, that's what it was that I was trying to understand. So what happens when we try to describe the behavior of things on a very small scale, such as the motions of electrons and atoms, we can't use the Newtonian rules to describe how things move through space. For really small-scale physics, I must use a new set of rules proposed in the early 1900s called quantum mechanics. Now, there's another situation where Newtonian physics is no good. That's when we want to describe the motions of objects near very large masses like stars and galaxies and black holes. We must use another theory developed in the early 1900s, Albert Einstein's theory of relativity. Now, quantum mechanics is a revolutionary way of thinking about particles. One of the major consequences of the theory is one cannot know both the position and the velocity of a particle precisely. Indeed, if one knows the velocity of a particle, then the particle does not even have a position. In such case, one can only speak of the probability of finding it. Quantum mechanics tells us that before performing an experiment, it might be better not to think of the particle as a particle at all, but as a not as a tiny dot, but as an entity like a cloud, which would be densest where is most likely to find the particle. And then relativity. Newton recognized that gravity caused an apple to fall from a tree, and the same force keeps the planets in orbit around the sun. He described it as an attractive mass force between two objects. But it describes objects falling to Earth and does a pretty good job at describing the planets around the sun. But Einstein came up with a deeper explanation of gravity. He says that massive objects actually curve the fabric of space. And you see this when you see scientific drawings, and they have this kind of grid work that goes out, and the balls of planets and stuff kind of sit in that grid work and cause a depression. And so an orbit is like us going down the drain in a sense. Now again, this is a two-dimension representation of four dimensions, but it's the closest that most of us can get around our mind around these things. And so people have wondered, what if we put these two theories together? Relativity tells us that space and time may be curved, and the curve gives us what we see as gravity. And mechanics tell us, among other things, that some things exist in an indefinite state. And uncertainties become very important when we try to precisely measure small objects. What are space and time like on a very tiny scale? Nobody knows for sure, but it seems fairly certain a theory describing nature of space-time on a small scale must have some of those aspects of quantum mechanics. And what this field of science is called is quantum gravity, trying to get these two different types of explanations to agree with each other. But it's easier said than done. Lee Smolin, in his book, 3 Roads to Quantum Gravity, explains why this is hard. Newton presumed 2 things. First, that space and time are fixed, like space exists like there is space in this room. It's what's inside a container. And secondly, that the observer is separate from the observed. Now, Einstein kept the assumption about the observer being different from the observed, but he changed that assumption about space and time. That space and time is not fixed, but relative. Hence, the theory is called relativity. Space is not a big room in which objects move. It is defined as the relationship between 2 objects. If there is only one object, then there is no such thing as space. You need that second object to create a relative space. And similarly, time is also relative. There's no cosmic clock sitting outside the universe saying what absolute time is. Time is just a measure of change between 2 objects, like our Earth going around the sun. Well, quantum mechanics, on the other hand, keeps Newton's expectation about space and time being fixed, but realizes that we can't separate the observer from the observed. When looking at the subatomic particles, scientists could find a position or the motion, but not at the same time. This is known as Heisenberg's uncertainty principle. Instead of being miniature solar systems with predictable orbits, atoms are fuzzy clouds of probability. What we see depends on when and how we look. Newton's universe, the one that I like and the one that I tend to live in, had constancy and objectivity. Einstein gave us relativity, but kept the objectivity. Heisenberg kept the constancy, but gave us uncertainty. Newton gave us one theory of everything, except the scientists kept on looking and found things that were too big to fit and too small to fit into this theory. So we used to have one theory, and now we have two, and they conflict. Physicists are searching for a unified theory that accounts for both relativity and uncertainty. Relativity and uncertainty. If ever there was a topic for a Unitarian Universalist sermon, relativity and uncertainty. One of the theories that attempts to explain and unify the two is string theory. See, the orbits of particles don't break Einstein's law of gravity. The particles don't behave as objects because they're not objects per se. They are one-dimensional strings. Of course, in all the drawings, to draw them, they show them as two-dimensional, so I'm not sure if I can get my mind around what is meant by one-dimensional string, because it seems like a point. But these are such tiny, tiny things, that the space between my fingers when I hold them as close together as I can. But these strings vibrate. And they look like different particles depending on how they vibrate. They may be protons and electrons and neutrons and gluons and all gravitons. And it tends on their vibrate. Now this, as a musician, it fits into all those poetic notions of the music of the spheres, that there's a vibration, and that we don't have these objects per se, but things vibrating at different rates. And another theory is loop theory. And this is a theory that space is not actually empty. When it takes Einstein's fabric of space-time, which he kind of perceived as kind of a unified sheet, and said, no, space contains particles too, like little threads, like little loops, something that's woven there, and that these particles of space, like particles of objects, act like that. They talk about the potential of every direction that one of these loops could go. And so that space has this, you can take a snapshot at it of any one time, but it doesn't really tell you what it is, because that only tells you what it is at one particular moment. And so you have all these different potentials and this fuzziness in space. So relativity, we don't know at this point. They are trying to come up with experiments that would say which is which. And no one knows if we're unified by string or tied up in loops. But both of these theories argue that there's a lot more stuff out there than we can see. And this is consistent with what the astronomers predict. We've wondered why that universe is expanding so slowly after the Big Bang. We see the stars moving, but there's not enough of them. The rest of this stuff is called dark matter, the mysterious force that holds the universe together, responsible for the creation of the universe, sustaining it beyond description, but necessary to make sense of our existence. Dark matter sounds a lot like a theory of God, especially to someone like me who looks at the mathematics and the physics theory behind it and says to take it on faith that these people must know what they're talking about. It takes as much faith for me to believe in the physics as it does for a God. But the question that interests me is, why are people working so hard to find a unified theory of how things are? And perhaps it's because we like to have one set of rules by which to live by. If we have more than that one possibility, we would have to wonder who chose the way we are living. Why would one law apply to galaxies and another one for atoms? If the laws are not universal, then they are selective. And then if they are selective, then someone must be doing the selecting. As if there is a God choosing to apply different laws to different situations. Lee Smolin writes, there seems to be only one possible answer to this question. Something external to the universe made the choice. If that is the way things turn out, then this is the exact point that science becomes religion. We like things to make sense. And our religion almost always reflects our science. Before the Enlightenment, God was much like a parent and was the one who caused the rain and caused the sun and caused the thing. That it was a person who was actively involved in every aspect of the day. But after Newtonian physics, there arose a religion of our founding fathers, deists like Thomas Jefferson and Ben Franklin. And they believed that Newton kind of had decoded the laws of God. As God applied the laws to the world to be observed and used by humans, the unified theory of Newton saw the universe as clockwork. If God was the great watchmaker, God then becomes unnecessary once we understood the watch. And thus came the rise of scientific humanism. But those scientists, they never stop asking questions. And that's when we discovered that the watch was illusory. Constancy and objectivity were replaced by relativity and uncertainty. If the new physics points to a new God or an intelligence that runs the universe, it will be a much different God than the God of our ancestors. One that takes into account uncertainty and relative ethics instead of universal laws. Smolin continues, so in the end, the most improbable and most puzzling aspect of space is its very existence. The great triumph of quantum gravity may be that it will explain to us why this is so. If quantum gravity does not, then the mystic who said God is all around us will have turned out to be right. But if we find a scientific explanation of the existence of space and so take the wind out of such a theistic mystic, there will still remain the mystic who preaches that God is nothing but the power of the universe as a whole to organize itself. In either case, the greatest gift of quantum theory of gravity would be a renewed appreciation of the miracle that the world exists at all, together with a renewed faith that at least some small aspect of this mystery may be comprehended. The bottom line is that most of us do not have the time to fully comprehend the physics or the theology of the universe. The discussions deal with such minutiae that take so much time to understand that what ultimately most of us have families to raise, jobs to do. And so we have to ultimately trust those minds who we perceive as greater than ours. In our day-to-day lives, we exercise our best theory of life, open to the reality that our truth might not be other people's truth. The difference between science and religion is that science claims to be open to revision, while religion tends to claim absolute unchanging truth. But when we look at the world, we often see scientists holding on to theories after there has been contrary evidence, and religions evolve. The Roman Catholic Church is not the same as it was 1,700 years ago. Hopefully, Unitarian Universalists find themselves well prepared to cope in a universe and or a God marked by relativity and uncertainty. May we be less committed to what should be and more interested in loving what is. May we live in fascination. It is worth it to travel to areas we do not understand. By observing reality, we might be changing reality, and at the very least, we change ourselves. We do not always see the interdependent web, but the strings and the loop bind us together in the fabric of space-time. Some things we know literally. Some knowledge is poetic. And sometimes all we can do is admire the mystery and the miracle of our existence. May we bless and be blessed.